Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will see that how to design the 4-bit adder and the subtractor circuit. And we will understand that using the same circuit, how we can do the addition as well as the subtraction. So we will understand this circuit in step by step. But first of all, let us see how to design the 4-bit subtractor circuit. So in the earlier videos, we already learned about the half adder and the full adder. And we have seen that by cascading 4 such full adder blocks, we can easily design the 4-bit adder. So after that, we have also seen the circuit for the half subtractor and the full subtractor. So similar to the adder circuit, by cascading n such full subtractor blocks, we can easily design the n-bit subtractor. And here, the design of the 4-bit subtractor is shown. So as you can see, here the 4 subtractors are connected in the parallel connection. And the output borrowed from the one subtractor is given as an input to the next subtractor. So this circuit performs the A minus B, where both A and B are the 4-bit numbers. So let's say the two numbers are 1110 and 0101. So if we perform the subtraction using this 4-bit subtractor, then for this first full subtractor block, this A0 is equal to 0, while this B0 is equal to 1. While the incoming borrow is already equal to 0. So here, this 0 minus 1 is equal to 1, and the output borrow will also be equal to 1. So now in the next column, this A1 is equal to 1, while the B1 is equal to 0, and the incoming borrow is also equal to 1. So here, this 1 minus 0 is equal to 1, and this 1 minus 1 is equal to 0. That means the difference is equal to 0, while the borrow is also equal to 0. So now in the next block, both A2 and B2 are 1. That means this 1 minus 1 is equal to 0. And since the incoming borrow is equal to 0, so this 0 minus 0 is also equal to 0. That means both difference and the borrow outputs are 0. So now in the final block, this A3 is equal to 1, while the B3 is equal to 0. And the incoming borrow is also equal to 0. That means here, this 1 minus 0 is equal to 1, and the outgoing borrow is equal to 0. That means the output is equal to 1001. So in this way, by cascading 4 such full subtractor blocks, we can easily design this 4-bit subtractor. So as per this design, if we want to do the addition and the subtraction of the 4-bit numbers, then we require 2 separate circuits. One circuit for the addition and one for the subtraction. So due to that, we require the more number of logic gates, and that will increase the cost and the complexity of the design. But what if we can perform the 2 separate operations using the single circuit? So that's exactly we are going to see next. So we will learn that how to perform the subtraction using the adder circuit. So that can be done with the help of the 2's complement. So let's say we want to subtract these 2 numbers. So in binary, these 2 numbers are 1110 and 0101. So instead of doing the subtraction, what we can do? We can add the number 14 to the 2's complement of the number 5. And for that, first of all, we need to find the 2's complement of the number 5. So if you know the shortcut method for finding the 2's complement, then this is the 2's complement of the number 5. That means starting from the LSB, just copy all the numbers as it is until you encounter the first one. And after that, replace all the ones by zeros and the zeros by 1. So here, the LSB itself is equal to 1. So we will keep it as it is. And after that, we will replace all the zeros by 1 and the ones by 0. So this is the 2's complement of the number 5. That means now, instead of doing the subtraction, we will do the addition of this number 14 and the 2's complement of the number 5. So here, this 0 plus 1 is equal to 1. Then in the next column, this 1 plus 1 is equal to 0, while the carry is equal to 1. Then in the next column, this 1 plus 1 is equal to 0, and the carry is equal to 1. And then in the last column, this 1 plus 1 plus 1 is equal to 1, and the outgoing carry is also equal to 1. So in this 2's complement form of addition, we will ignore the outgoing carry, and the remaining number is our result, that is equal to 1001, and in the decimal this 1001 is equal to 9, and that is our correct result. So in this way, by using this 2's complement method, we can easily convert the subtraction into the addition. So for that, we need to convert the number into the 2's complement form. So now, let us see the digital circuit which can perform the 2's complement of the given number. So let's say we want to find the 2's complement of the given number. Now using the shortcut method, we already know that how to find the 2's complement. But actually what we are doing, we are finding the 1's complement of the given number, and then we are adding the 1 to that number. So the resultant is the 2's complement of the given number. So in this way, we are actually finding the 2's complement of the given number. So here, using the NOT gates, we can find the 1's complement of the given number, because in this 1's complement, we are replacing the 1's by zeros and the zeros by 1. So that can be done using the NOT gates. And after that, we just need to add the 1. So this is the circuit using which we can perform the subtraction using the adder circuit. So here, using these 4 NOT gates, we are converting the number b into the 1's complement form. And here, by making this C0 is equal to 1, we are effectively adding 1 to that 1's complement number. That means if we see the overall result, then that is equal to A0 plus 2's complement of the number b. So in this way, we can use the adder circuit for performing the subtraction. So let us take one example, and through that example, let us understand the working of this circuit. So let's say we want to do the subtraction of these two numbers. So in binary, these two numbers are 1100 and 0111. So here, instead of performing the subtraction, we will do the addition of this number 12 with the 2's complement of the number 7. So we know that the 2's complement of this number 7 is equal to 1001. That means effectively, this 12 minus 7 is equal to 1100 plus 1001. So here, this 0 plus 1 is equal to 1, while this 0 plus 0 is equal to 0. Then in the next column, this 1 plus 0 is equal to 1, and in the final column, this 1 plus 1 is equal to 0 with 1 as a carry. And here, we will ignore the final carry. That means the final result is equal to 0101, and in the decimal, that is equal to 5. So let us see how the circuit performs the same operation. So here, the one number is 1100 or the 12, while the second number is 7, that is equal to 0111. So once it is passed through the NOT gate, then all the zeros will get converted to 1 and the ones will get converted to 0. And here, this incoming carry to the first adder is equal to 1. That means now, this 0 plus 1 is equal to 1. That means the output of the first adder is equal to 1, while the outgoing carry is equal to 0. So now for the next full adder, this 0 plus 0 plus 0 is equal to 0, and the outgoing carry is also equal to 0. So if we move to the next full adder, then here these 0 plus 1 plus 0 is equal to 1, while the outgoing carry is equal to 0. And now in the final full adder, these 1 plus 1 is equal to 0, while the outgoing carry is equal to 1. But since we are performing the subtraction, so we will ignore this final carry. That means the result is equal to 0101, and that is equal to 5. So this is how we can use the adder circuit for performing the subtraction. Alright, so now let us modify this circuit little bit so that we can perform the addition as well as the subtraction using the same circuit. So for that, here we require the control circuit. So whenever we are performing the addition, then all the B inputs should pass as it is. But when we are performing the subtraction, then here we should get the inverted outputs. So here this control circuit should be such that based on this control input, it will provide either B or the complement of the B. And for that, first of all, let us see what should be this control circuit. So we already know about the XOR gate, right? So in the XOR gate, if one input is A and the second input is 0, then the output of the XOR gate will be equal to this A dot 0 bar plus A bar dot 0, and that is equal to A dot 1. That means whenever one of the input to the XOR gate is equal to 0, then the output is same as the other input. Likewise, when one of the input to the XOR gate is A and the second input is 1, then its output can be written as A dot 1 bar plus A bar dot 1, and that is equal to A bar. That means whenever one of the input to the XOR gate is 1, then its output is the complement of the one of the input. So similarly, if the two inputs to the XOR gate are A and the control input, then its output can be written as this A dot control bar plus A bar dot control input. That means whenever this control input is equal to 0, then the output is same as the A, and whenever this control input is equal to 1, then the output of the XOR gate is equal to A bar. That means by controlling this control input, we can decide whether the output is A or A bar. That means for our purpose, we can use this XOR gate. That means whenever this control input is equal to 1, then the output of the XOR gate is the complement of the number B. And whenever this control input is equal to 0, then the output will be same as the input. And here, this control input is also given as an input to this C0. That means whenever we want to perform the addition, then this C0 is equal to 0, and all the XOR gates will pass the B input as it is. But when we want to perform the subtraction, then this control input should be equal to 1. So in that case, this C0 is also equal to 1, and the output of this XOR gate is the complement of the number B. So in this way, this circuit will work as an adder as well as the subtractor. So let us understand the working of this circuit using the examples. So first let us see the example of the addition. So let's say we want to add these two numbers. So in binary, these two numbers are 1100 and 0111. That means here the number B is equal to 0111 and the number A is equal to 1100. Moreover, since we are doing the addition, so this control input is also equal to 0. So because of that, all the bits B3, B2, B1 and B0 will pass as it is. And this C0 is also equal to 0. So now for the first full adder, this 1 plus 0 is equal to 1 and the outgoing carry is equal to 0. Then if we move to the next adder, then this 1 plus 0 is equal to 1 and the outgoing carry is equal to 0. Then for the next full adder, this 1 plus 1 is equal to 0 while the outgoing carry is equal to 1. And for the final full adder, this 1 plus 1 is equal to 0 with 1 as a carry. That means the final result is equal to 10011, and that is the addition of these two numbers. So in this way, by making this control input is equal to 0, we can perform the addition. Similarly, let us see how we can perform the subtraction. So let's say for the same numbers, now we want to do the subtraction. So in binary, these two numbers can be written like this. So here effectively what we are doing, we are adding the number 12 with the 2's complement of the number 7. And the 2's complement of the number 7 is equal to 1001. That means effectively we are adding this 1100 with 1001. And earlier as we have seen, the result should be equal to 0101. So let us see the same thing with the circuit. So here one of the input is equal to 0111 and the second input is 1100. And here since we are performing the subtraction, so this control input is also equal to 1. That means here this C0 is also equal to 1. And here since the control input is equal to 1, so the output of this XOR gate will be the complement of this B3, B2, B1 and B0. So now this adder circuit will add all these numbers. So for the first full adder, this 0 plus 0 is equal to 0 and this incoming carry is equal to 1. That means this 0 plus 1 is equal to 1 while the outgoing carry is equal to 0. Then for the next full adder, this 0 plus 0 plus 0 is equal to 0 and the outgoing carry will also be equal to 0. So if we move to the next adder, then this 0 plus 1 is equal to 1, while the outgoing carry is equal to 0. And now for the final full adder, this 1 plus 1 is equal to 0, while the outgoing carry is equal to 1. And since we are performing the subtraction, so we will ignore this output carry. That means the output result is equal to 0, 1, 0, 1. So in this way, by making this control input is equal to 1, we can also perform the subtraction. That means by using these XOR gates along with this control input, we can use the adder circuit for the addition as well as the subtraction. Alright, so now so far in our discussion, we have only assumed that the number A is greater than B. But we can also have the other case where this A is less than B. So let us also consider this scenario. So let's say the number A is equal to 10 while the number B is equal to 12. So in binary, that is equal to 1010 and 1100. So in this case, if we perform the subtraction using the 2's complement form, then what we are doing, we are adding the 10 with the 2's complement of the number 12. And as you know, the 2's complement of the number 12 is equal to 0100. That means effectively, we are adding this 1010 with 0100. So if we do the addition, then here this 0 plus 0 is equal to 0, while this 1 plus 0 is equal to 1. Similarly, in the next two columns, we will also get this 1. But here as you can see, the outgoing carry is equal to 0, which indicates that the result is in the 2's complement form. So let us see how the circuit performs the same thing. So here, one number is 1100 while the second number is 1010. And since we are performing the subtraction, so this control input will be equal to 1. And since the control input is equal to 1, so all the B inputs will get inverted after this XOR gate. So now for the first adder, the inputs are 1 and 0 and the incoming carry is also equal to 1. So here this 1 plus 1 is equal to 0 with 1 as a carry. So in the next adder, this 1 plus 1 plus 1 is equal to 1 with the outgoing carry is also equal to 1. Then in the next adder, this 0 plus 0 plus 1 is equal to 1 with outgoing carry as 0. And then in the last adder, this 0 plus 1 plus 0 is equal to 1 with outgoing carry as 0. So this is the result after the subtraction. And as you can see, here there is no outgoing carry. That means the given result is in the 2's complement form. But just by looking at the result, how do we know that the result is in the 2's complement form? So for that, we just need to see this control input as well as this outgoing carry. So whenever this control input is equal to 1, that means we are performing the subtraction. And in that case also, whenever this A is less than B, then this outgoing carry C4 is equal to 0. So just by looking at these two signals, we can know that the result is in the 2's complement form. So to indicate that state, we can add this little circuit to this existing circuit. So here, the output will be in the 2's complement form when this C4 is equal to 0 and this control input is equal to 1. So in this condition only, the output of this AND gate will become 1 and it will indicate that the result is in the 2's complement form. So in this way, by adding this AND gate and the NOT gate, we can also get the indication for this output result. That means whether the output result is in the 2's complement form or in the normal form. So the same circuit can also be represented like this. So here, instead of showing the 4 different full adder blocks, I have combined it into the single block. So using this control input as well as the XOR gate, we can perform the addition as well as the subtraction. And using this one more AND gate and the NOT gate, we can also get the indication for the 2's complement result. But in addition to that, suppose if we want to convert the 2's complement result into the true form, then we can also do that by adding this little more circuit. So here, to convert the 2's complement result into the true form, here one more adder circuit is used. So here, this XOR gate will perform the 1's complement and then by adding 1 to it, we will get the 2's complement of the overall result. So whenever this A is less than B and we are performing the subtraction, then this output will become 1. That means the incoming carry to this second adder is equal to 1. Moreover, in this case, This XOR gate will also perform the ones complement. Moreover, we can also use the output of this AND gate as the sign bit, which will indicate that the result is negative. So this is how, using the adder circuit itself, we can perform the addition as well as the subtraction. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.